Hello and welcome. In today's lecture we're going to continue to add new tools to our circuit analysis toolkit, and in particular I've broken these lectures down into two segments, part A and part B, to discuss circuit theorems. We'll talk about why these theorems are important, but to give you a summary of what we're going to be discussing in this particular section of the lecture, lecture 12A, they're going to be an introduction to the concept of circuit theorems and why they're needed. We then are going to discuss the definition of linearity and the application to linear circuits that we have considered thus far. We're then going to look at the idea of superposition principle and when we can use that. Then we're going to look at source transformation and kind of motivate the reasoning for using this technique. We're then going to look at examples for each case, and we're going to take a quiz as usual to reinforce the concepts. And one last point is that you have to make sure that you're pretty comfortable with the prerequisite concepts that are written here. By doing so, you will get the most out of these lectures. So let's go ahead and talk about kind of motivate why we're looking into this topic. So the theory we've developed thus far only helps us in solving simple circuits, resistive circuits, circuits with voltage and current sources, both independent and dependent. But the question we have to ask ourselves is that, is it practical to apply mesh and nodal analysis techniques that we've learned so far to large circuits that can contain hundreds or thousands of passive and active elements, so resistors, inductors, capacitors, transistors, diodes, and so on and so forth? Is it really practical to go there and kind of break, let's say, 20 meshes, separate 20 different meshes and solve it by hand or even by matrix methods? So further considering that question, we can also ask a follow-up question, which is that what can we add to our circuit analysis toolkit to be able to analyze circuits with increasing complexity? And the reason we're asking this question is that we have to consider that electrical engineers are very interested in simplifying and developing equivalent models for complex circuits. So in other words, we like to simplify complex circuits and develop equivalent models for them. So from the very beginning we've seen this, right? So we've seen that if you have a simple resistive network containing 4 resistors, R1 through R4, we look at terminal behavior. So we look at its terminals and consider what is the simplest possible representation of this circuit that can kind of produce the same behavior. So what is behavior? It's essentially IV characteristics, voltage and current characteristics at some particular terminals. So in this particular case, if I apply a certain voltage, I would get an equivalent, a certain amount of current flowing into those terminals and coming back out from terminal B, for example. And if I apply a current source, the current is going to flow through the circuit and develop a certain voltage across terminals A and B. Well, this can be modeled by one single resistor that is a function of each of these individual resistors. And you can watch the previous lectures again and use those techniques to find these. So using this simple example to show you why we want to do this, I'm trying to prime your mind for kind of appreciating why we need to get into this subject. And so to answer our previous question, it is not practical to have a circuit of, let's say, 10-20 meshes or 10-20 nodes and higher and apply nodal and mesh analysis to every single node or mesh. It becomes very time consuming, and practically speaking, you're not going to be able to get anything done efficiently, at least at those rates. And so the concept is, okay, let me look at this simple circuit here that consists of 2 independent current sources and 1 voltage source and some resistors, and think of its terminal behavior. How does its terminal behave if I give it some voltage or current at those terminals and want to look at output, either current or voltage? So the question then is, similarly to the case above that we've considered many times, can I simplify this circuit into some independent source, voltage or current source, and some element, resistor or whatnot? Let's keep it general for now. So in other words, can I look at this as a black box and express its behavior as a function of its internal components in the simplest manner possible? So that's kind of the question we need to consider throughout these lectures. So with that being given to us, let's go ahead and consider the idea of linearity while you think of those concepts. So for a linear circuit, the output voltage or current must be a linear combination of the input voltage or current, or the input excitation. So if we consider the same circuit, some circuit here that has some factor that's multiplied by the input, let's say gain or attenuation or whatnot, depending on what the circuit is. Let's just say the system, let's call it system factor or system multiplier. If we give it an excitation Vn1, which is some constant alpha times some input voltage, for example, Vs, then the output's going to be Vo1, which is the system multiplier times the input, in this case alpha Vs. In another scenario, if we apply Vn2, which is beta Vs, we would expect to get Vout2 equals the same system multiplier times the second input, beta Vs. Now, in all of these cases, what we basically want to do is we want to prove that if I apply a sum of these scaled inputs, I should be able to get the sum of scaled outputs. So, in other words, if I have Vn3, which is a sum of two input voltages, Vn1 and Vn2, I should be able to see that Vout3 is some linear multiple of these two inputs. That's a very simple concept, and to prove it, you essentially, to look at the actual math, you essentially say, okay, I've defined Vn1, and I know what Vout1 is going to be. I've defined Vn2, and so on and so forth. And if I have Vn3, which is a sum of the two inputs, I would express what I would expect the total input to be, so alpha Vs plus beta Vs. Then I apply that to the system, and I would get, you would get at the output A times Vn3. That's what you would expect. Vout3 should be A times Vn3. Now Vn3 is alpha plus beta times Vs, same thing as here. If I plug that into the expression for the input, I would have A times alpha plus B times Vs. I can put another parenthesis here to make it clear. And factoring those out, we would get the following result. Now alpha Vs is simply Vn1, beta Vs is simply Vn2, and so we can simplify the entire expression as Vout3 is equal to A Vn1 plus A Vn2. So this has proven that the system is linear. You can also express this as, you can factor the A out and say Vn1 plus Vn2. So it is very simple to show in these circuits that they are linear. So let's go ahead and look at another kind of concrete example with variables or numbers. Okay, so here we have a very simple example, a simple resistive network. I've drawn some dotted lines here to indicate that this is a black box system. We want to start thinking about linear systems that way. They're black boxes, and you look at their terminals, you apply some excitation, current, or voltage, and you look at the output and see the effect. So I want to get us to think that way about these systems. So in this case, we're asked to prove that the simple resistive network is linear. So given the definition we've seen so far, what we would do is we say, okay, we have some input voltage. I can create two different inputs. Vn1 is equal to alpha Vs. Vn2 is equal to beta Vs. So some factor, 1 volt, 2 volt, 10 volts. You can change the voltage as the system permits, and we can say that Vn3 is going to be the linear combination of these two inputs. And so we need to show that the output is going to be some system multiplier or some sort of factor times or a linear multiplier times the two inputs that were individually applied to the system. Because Vn1, we expect Vout1 to be A times Vn1, and we expect Vout2 to be A times Vn2. And so let's go ahead and actually apply it to this very simple system. So in the first case, we can apply a voltage divider. It's very simple. V out 1 is equal to R2 over R1 plus R2 multiplied by the input, which is alpha Vs. And in the second case, we can apply a different voltage. V out, the output's going to be R2 over R1 plus R2, and this in this case this would be our A, or the system gain or attenuation, the same A here. And the second input is going to be beta Vs. Now the question is VO3 equal to VO1 plus VO2? That's the question. And so to find that, what we would do is we would apply Vn3, which is simply alpha Vs plus beta Vs. We would apply that to the system, and the question is when we do that. So let's go ahead and so we know that's going to be the form Vn3, and A is going to be, let me just continue to write everything out. So alpha Vs plus beta Vs. So we know what our system factor is. It's going to be R2 over R1 plus R2, simple voltage divider. And we have our alpha Vs plus beta Vs. And writing all that out, we have alpha Vs R over R2 over R1 plus R2. Okay, so that's our final answer, and just to simplify it a little bit and summarize it, so VO3 we have proven that it is simply A times alpha Vs plus A times beta Vs, which is equal to A Vn1 plus A Vn2. So we have proven that the system is linear. So it's very simple, and I would hope that you can get very comfortable with this as we move forward, because the next concept is the superposition principle. So the linearity property leads us to one of the consequences of linearity is that is the superposition principle. And basically what it is that if you have n different sources that act on a system, so let's say it's a voltage or current source, when they act on a system to produce a particular effect at the output, that effect can be also found by considering one source at a time and summing the result of each source at the output. So what do I mean by that? So how would you actually apply this to, let's say, this circuit? What you would do is you would turn off all independent voltage and current sources. The keyword is independent, and except for one of the sources, so either current or voltage sources that remain, you want to just keep one on at a time. You want to find the output variable, whether it's current or voltage, as a result of that active component, active source, using the nodal or mesh analysis techniques that we've learned and discussed many times. Then we want to repeat that first step for every single remaining independent source. And once we've done that, we can then calculate the output variable by summing the individual contributions of each independent source. We're going to look at examples, so don't worry if you don't fully get this yet. Now, a particular note is that we cannot suppress dependent sources. If we suppress them, well, the reason we can't do that is because their contributions depend on independent voltage or current sources, and so if we suppress them, we're not accurately accounting for their effect into the circuit. So the rule here is that you do not suppress dependent sources. So if you look at this example, you do not suppress this guy. You simply leave this voltage controlled current source, or sorry, current controlled voltage source. You leave this guy be, and you do not ever suppress it. You only suppress the independent sources one at a time. So with the output variable being the current in this particular branch, the way I like to express the superposition principle is that the output current is the output current when the current source is off plus the output current when the voltage source is off. And let's talk about how do we actually turn these off. So we need to find I/O when I first turn off the current source, and the way we do that for current sources is we open them, so we essentially simply break the connection so that no current can flow, such that it's 0. So that's the first case. So once we do this, so let me label that as the first case. We break that particular node, and we find I out by doing the mesh or nodal analysis techniques in the remainder of the circuit. And in the second case, we zero out this voltage source, but we put back the current source. So the first case, we got this guy out. Now the second case, we zero out the voltage source. The way you do that is you simply short a voltage source out on paper. So you don't do this in real life, you only do it on paper. We short this guy out, and by shorting it, we zero out that voltage across these nodes. Once we do that, this guy simply turns into just a line basically, and then we again find I out, which is this particular I out, by doing mesh or nodal analysis techniques. Okay, so here's another simple example that we're going to apply superposition principle to. So looking at this circuit, we see in the two independent sources, and there's an output variable that we need to find. And so if you just take away this independent current source, you have a simple voltage divider. And if you remove this particular voltage source, you have a simple current divider. So normally the way you would do this is you would apply KCL. In this particular case, you would simply apply KCL. So this node voltage minus this node voltage VO over that resistor, is equal to 5 amps plus or minus this particular current going into this resistor. So you could do that, but for this simple example, that would work. But as we get to more complex examples, it becomes very cumbersome. So to use the superposition principle, which is what we're asked to do here, we would say, okay, the output variable is V out, so I'm going to need to look for V out. But I'm going to do that when V out, I'm going to find first V out when the source voltage is equal to 0. And I'm going to sum that with the V out when the source current is equal to 0. Let's call that IS. So let's go ahead and draw the equivalent circuits for these two cases. So that's case 1, that's case 2. Let's go ahead and draw that out. Okay, so as you can see, for the first case, as I've defined here, it's V out when Vs is equal to 0. To zero out a voltage source, independent voltage source, we simply short out that voltage source. We take it out, we short what was remaining in its place, and we leave the other source, and we carefully label the output as the V out under that particular condition. So V out when Vs is equal to 0. We look at the second case, we keep the first the voltage source intact, and we take out the current source. How do we zero out current sources? We simply remove them. Because an open circuit causes no current to be flowing, and so that's when a zero current condition occurs. And we again carefully label its output. So these are not V out. These are simply V out under a given imposed condition that we applied to it. So what we do is we simply consider these two cases, apply superposition to it. So the first case, let's look at it. What would the output voltage be? Well, we know when this current flows, the 5 amps flows up here, it can only go through these two resistors, and we can simply, for the first resistor, which V out develops across it, we are given the polarity, the passive sign convention, and so this polarity assumes that the current flows down to R2, and I'm simply going to do the same sort of logical assumption here and assume that the current is going to flow here and cause a voltage drop. So let's do that for the first case. So let's consider what happens. We have this current flowing through both elements, and we need to find V out. So what I can do is I can use current divider. So I can say that V out is equal to 5 amps. Now recall that current divider is slightly different from the voltage divider. If you have two resistors like this, for voltage divider you would say that the output voltage gets divided down by the ratio of R2 over R1 plus R2. But for current divider, it's the other resistor comes up top. So what does that mean? If you think about this intuitively, we're saying how much voltage develops across R2. Well, that depends on how large R1 is. If R1 is very large, most of the current flows through this resistor R2, because current, if you want to think about it simplistically right now, at this level, current follows the path of least resistance. And so imagine R1 being an open circuit, so being infinite resistance or a very large resistance. What you would expect is that most of the current flows through R2. That's what would happen. Let's say R2 is 1 ohm and R1 is let's say 100 megaohms, and so you would expect almost 5 amps, a very large portion of 5 amps, maybe 4.99 amps, to flow through R2. And so this equation reflects that. If R1 gets huge, let's take the limit of V out as R1 approaches infinity. What would you get? You would get 5 amps times, let's factor R1 out, R1 over R1 multiplied by 1 over 1 plus R2 over R1. Well, if you're taking the limit as R1 approaches infinity, we can cancel those guys out, and R1 goes to infinity, this goes to 0, and we get 5 amps, which makes sense. Intuitively and mathematically, we have proven that. And so that's how I think about current divider, is that it's the other guy's resistance, it goes into the numerator. If you don't like it this way, what you can do is you can simply combine these two resistances. So let's actually calculate the value first before we do the other method. We simply calculate this 5 amps times 10 over 10 plus 5, which is 15. That is simply 1/3, so that's going to be 5/3 of an amp. 5/3 of a volt. Always check your dimensions. So we have 10 over 10. Let's see here. Sorry, so it looks like I'm forgetting something. So I'm forgetting to, once I found this current, I'm forgetting to multiply that by the resistor value. So I forgot to multiply by the resistor value times R2. So I hope that didn't confuse you. So the current divider simply tells us how much current is in the, so what I should really be saying is that the current through this branch is going to be 5 amps times R1 over R1 plus R2. So that's only the current. It's getting divided down by a factor. And the voltage then, V out, is going to be that current multiplied by that resistance. And so you can see here what we have done. So let's kind of log that out. And hopefully this makes sense to you. So the limit, so if R1 was an open circuit, and let's say R2 remained 5 ohms, V out would become 5 times 5, 25 volts. This makes sense. So now, but now it's getting divided down because R1 is a finite value, so some current's going to be stolen in the other direction. So not all the current's going to go through R2. And so the 5 amps is going to get divided down by this factor of 1/3, but then it's going to have to be multiplied by the 5 ohm resistor to become the output voltage. And so what this does is you can cancel these out, and you would still get, let's see, am I doing this correctly? 5 1/3, 50 over 3 now. So 50 over 3 volts. And so that's the first case. And in the second case, let's see here. In the second case, and actually we found a value here. So what I was going to consider here is that the other method for doing this is that you could simply turn this into an equivalent resistance. So you could turn this into the equivalent of R1 and R2, which is somewhere in between 5 and 10. So you could say R equivalent is equal to 5 times 10 over 5 plus 10. So that's 50 over 15. And what you could do then is you could have the current, all the 5 amps, flow through this one resistor that's equivalent. And what you would get is that now the problem with that is if you do that, let's see, no, that should be the same, okay, because V out, these are in parallel, and so the V out across this guy is the same as the V out across the other guy, and so you can do this easily. So the V out is going to be R equivalent times the 5 amps, which is 50 over 15 times the 5 amps. These cancel, you get 50 over thirds, 50 thirds volt. Let's take that out. This got really messy, I apologize, but I hope you get the concept. These are the same with two different methods. So looking at the second section of this superposition problem, we have to then simply apply a voltage divider. And so let's still correct one more thing. So this is V out when the voltage source is equal to 0. So let's keep that in mind. So then we find V out when the current source is equal to 0, and you can see I've taken it out here. And we can simply do a voltage divider, and that is, let's just say this, V out when that is the case, it would be Vs times R2 over R1 plus R2, which is 10 volts times 5 over 5 plus 10, which is 50 over 15 volts. You can simplify that a bit. Factor of 5 out, you get, and factor of 5 out here, you get 10 over 3. Let's see, 5, right. 10 over 3 volts. And so the final answer then is that the output voltage is equal to the first case plus the second case. So you have 50 over 3 plus 10 over 3, which is equal to 60 over 3, which is equal to 20 volts. V out is equal to 20 volts using the superposition principle. Let's go ahead and verify this with LT Spice. Okay, so you can see the circuit here, a very simple circuit. I've labeled this node V out, and I'm running a simple DC operating point, and I'm going to run it. Look at V out, and I see 20 volts as expected. Okay, so let's go ahead and talk about the idea of source transformation. As you recall, linearity is the backbone of the superposition principle, and the principle of equivalence between terminals, so equivalent behavior between one circuit and another at its terminals, is the backbone of source transformation. And so let's talk about the reason why you might want to actually do a source transformation. So if you keep in mind linearity and equivalence, you're able to transform a voltage source into a current source and vice versa. There are two conditions that you must follow to be able to do this. So the first one is that the voltage and current sources cannot be ideal, and we'll see why that is. So they have to be practical sources with some loss. And recall that losses are usually modeled by resistors. And the second condition is that the polarities must be considered carefully. So you definitely have to pay attention to the polarities of the voltage source or the direction of the current flow. So before we get into that, let's go ahead and look at a practical voltage source and a practical current source. So a practical voltage source, if we recall the ideal one, an ideal voltage source would simply look like this. It would have just your positive and negative terminals, and then they would go into, you would basically measure them at terminals A and B, and it would give you exactly your desired voltage no matter what the load is. So as you increase or decrease RL, if you short it, if you set RL to 0, of course it's going to be 0 here, the output, but besides that, essentially you will always get Vs across RL, and you will get the desired current by Ohm's law. But in the real world, your batteries, for example, have internal resistances, internal losses, whether that's from the finite conductivity of the conductor connecting the terminals, or just any other parasitic resistance inside could give you this source resistance that is modeled by one single resistor here. And essentially what this is going to do is create a voltage divider between your battery or voltage source and the load. And so what would you expect from that? What you would expect is that if you start with a short circuit at the output, you would start with 0 volts, of course, and you can look at the equation here with the voltage divider, and you can see if RL is equal to 0, you get 0 volts at the output. As you increase RL, if you take it to infinity, you would get, at the limit, you would get a 1/1 ratio, and so at an open circuit for RL, you would get Vs, and that makes sense because you would have no current flow with an open circuit at the output, and therefore there's no voltage drop at RS. But in reality, we never really want to just keep such circuits open. We want to use them across a load, and so the practical voltages in their resistance, then the parasitic resistance kind of degrade the performance. And so if you look at a current source, a practical current source, is going to have a parallel element here that is also some finite resistance. And how would it behave if you have a short circuit? Well, the entire current is going to essentially short this resistor and appear at the output. And so you can see in the graph here, at a short load, you would get IS, and of course as RL goes to infinity, becomes an open circuit, none of the output current shows up at the output, and all of it goes through that. It basically burns up inside that current source, and you can see that here. So there's kind of a reciprocal, somewhat of a reciprocal relationship or inverse relationship between these two different sources. And so given that background, source transformation is basically the idea that if you have a voltage source and a resistor in series with it, you can turn that into a current source with a resistor in parallel with it. And the way you relate them is that if I start with the voltage source, the current source value becomes Vs over R. And of course pay attention to the directions. So your plus and minus going this way, and your current will go upwards here. You'll of course have the same resistor in both cases. And now if you start with the current source and go to the voltage source, you would then get, so if I started here instead with some IS is equal to, let's say, 1 or 2 amps, for example, what you would have is that I would pay attention to the polarity and place the same resistor here, and then I would simply do I times R by Ohm's law. So V would be, for example, 2 amps times R, and that would be the voltage you would need to supply to get a desired voltage. So let's check, kind of conceptually, let's check what that means and how does that make sense. So we can see here that whatever the current is, if you have some sort of a load here, whatever the current is flowing in this circuit, there's going to be some voltage drop across that resistor. And if you don't have a load and you simply have, let's see, you simply have this Vs over R here, you can see that if there's no load across these terminals, you would have the entire IS flowing through this resistor R, and we can find the output voltage in that way. And so the output voltage would be IS, which is Vs over R, multiplied by R, and that would simply be Vs. So you can see that in an open circuit condition, this is exactly the same thing as this original circuit in the open circuit condition, because if there's no current flowing in this direction, the entire voltage would appear here, because there would be no voltage drop as a result of current flowing through R. And so these are the basics of source transformation. So let's go ahead and take a look at an example here, a prominent example. So if you're asked to find the output current here by source transformation only, so we can't do any other techniques. So go ahead and pause the video and try this yourself, and then watch me do it. Okay, so assuming that you've tried it for yourself, let's go ahead and actually solve this. So I know I'd like to find the current through this branch, and so I'm just going to leave that branch alone. And I am going to note that the assumption here is this particular polarity because of that current flow. And so I'm just going to leave that branch alone and just work on everything else. So let's think here. I see a current source. I'm going to think about where its current would potentially be going. The current could be going this way, this way, this way, and elsewhere, of course. Let's think about it. Would it change anything? Would the IV characteristics change at these terminals if I swap these guys around, the resistors and the current source? Would any of that change? Well, if you think about it, no, because if you disconnect everything here and you swap these guys around, the currents will move in whichever way they should, because all these elements are in parallel. And so whatever that voltage is, let's call it VA for example, depending on how this current flows when it's unconnected here, it is going to be what it is no matter where you put any one of these elements. And so given that, and by combining these guys together because they're in series, we can go ahead and simplify these segments of the circuit. So I'm going to source transform these sections. Okay, so once again, what I did is that I moved the current source here to the very left and moved the 10 ohm resistor to the right to be able to clearly see that I'm going to have a 2 amp source going through these resistors to the 10 ohm and the 5 ohm. Then I simply combined the 10 and the 5 to get roughly 3.33 ohms here. Now, the way we do source transformation is we check the direction of the current or voltage polarity, and in this case it's going up, so I know my voltage source is going to have a typical positive negative in this fashion. Then I multiply the current times the equivalent resistance per Ohm's law, and that is 2 times 3.33, which is about 6.66 or so repeating. But we're going to round that kind of down, of course, and stop it somewhere. And so that is what we have. We keep the same resistor as the equivalent resistance here in series with the voltage source, and now we have the values, and we keep this guy the same. We don't change this guy because we need that current. And I do the same thing here. I find 5 ohms here, move it kind of to the other side so that I can source transform the 5 amp current in those guys, and I get 5 times 5, which is 25 volts per Ohm's law, and I keep the same resistance, the 5 ohms. And now basically what we need to do is get everything to be a single mesh, so that actually we're not going to do a mesh because we can't change this guy. And so what we can then do is move this guy back here, and the reason we can do that is that if you think about it, and if you're writing the mesh equation for this first mesh only, think about what you would see as you go up. You would go up and see a negative 6.66 volts or so roughly. Then if I assign this polarity here, I would see positive 3.33i. Then I would see a negative 10 here. Let's ignore everything else because it doesn't change for this particular step. And so it's going to be dot 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 equals 0, whatever it may be. If you think about it, if I take the 10 volts here and move it, the 10 volt source, and put it here, let's see if anything changes. Would the current change? Well, no, because we know that all series elements share the same current, and so I can swap all of these guys around and nothing should change in terms of current. So the mesh current should stay the same. Now, what about potentials, the voltages in the loop? Would that change? Well, let's think about it. If I put this guy here, I would see this source first, then the next source, and then the resistor. What would that do? Well, I would see a negative 6.66, then I would see a 10 volts, then I would see the current or the resistance value, the voltage across the resistor, and then that's it. So nothing has changed here. I've only changed the order of operations for the order of basically addition and subtraction. So that's kind of my small proof and mini proof for you that the reason you can do that. you can move the source around. Okay, so in this case I've gone ahead and moved the 10 volt source to the very left of the resistor. Then I've combined the voltages, because you can do that. If you recall the mesh equation again, you would see a negative, hold on one sec, you would see the negative 6.66 as you go up. Then you would see the moved voltage, which is negative 10. Now I can simply just combine the two and get a negative 16.66 as I go up from the bottom. And so that's what I've done here. The math kind of shows you that conservation of energy is still applied here, and it's not violated. And so continuing forward now, because we can't move this guy, we can't really change it much if you want to keep things convenient. What we can do is do another source transformation here and get everything to be in terms of current sources. If we do that, we get the following circuit. Okay, so having simplified this circuit by doing two source transformations once more, you can turn this into a current source in parallel with a resistance, and paying attention to the direction of the voltage source. Plus and minus in this fashion would give you a current flowing in the upwards direction. Now, of course, using Ohm's law, you would expect the current to be V over R, and so of course the resistance remains the same, 3.33. The current through that current source will be the voltage divided by the resistance, and that's roughly 5 amps here. And we have the voltage divided by the resistance once more, that's about 5 amps. And now we can essentially combine these two current sources, because all they're doing and how they're affecting the circuit is that they're pushing 5 amps from both directions, and that current is going to split in some fashion between all of these resistors. So we're basically going to combine them, and a small proof for why that's okay is that this is all the same node, and so you can imagine that if this whole thing is the same node, so we can call it Vx, and you have 5 amps going this way, 5 amps going in this direction. And so if I simply move this guy to the very left here near the other source, or vice versa, I haven't really done anything differently. I'm still, let me simplify this once more. So I have some node here, Vx. Right now I have 5 amps flowing this way, 5 amps flowing this way, and some mystery current, which really the sum should be 10 amps and if things are going in the right direction, if the assumption is correct for the direction. And if that is the case, that would be 10 amps. Now let's think about it. If I simply move this source to the other side, I would simply have 5 amps there, 5 amps there, going into that same node, and I would still have 10 amps going through that node. And so you can see that nothing has changed. So I'll go ahead and do that, and I will also combine these resistances, the 5 and the 3.33 in parallel, but keep this guy the same, and you'll see why I'm doing that. Okay, so I have combined the two current sources by the logic I just mentioned and explained, and I've also combined these two resistors in parallel to get roughly 2 ohms. And so voila, you can see that the circuit is very simple. All we have to do is do a simple current divider, and if you recall, the current through this branch IO is simply going to be the source current 10 amps multiplied by some resistive ratio. It's not like the voltage divider, is slightly different. So the current going through this resistor is proportional to the current or the resistance of the other paths in the resistive. Let me rephrase that. So the current going through a given resistance in parallel with other resistors is going to be proportional to the resistance of other resistors, basically. So, and I've explained that in a few minutes ago why that is, with the current taking the path of least resistance. And so the other resistor is 2 ohms, and if you sum those up, 2 plus 5, you would have 10 times 2 over 7, which is 20 over 7, and that gives us an output current of roughly 2.86 amps. And what we're going to do is go ahead and use LT-Spice to verify this very quickly. Okay, so we have the original circuit right here, and I have the current directions being the negative of negative 2 times. Let's see here, did I do it correctly? Right, so they're going up here, and so if you do a negative for a downgoing current, it should be the same. And let's get it back again, and let's run the DC operating point simulation. And if you look at the current through R3, which is a 5 ohm resistor, you would see 2.85, which is very close to our answer, and so we've done it correctly. Now let's go ahead and move on to the quiz. Alright, so now we have gotten to the quiz portion, and for the first question we're asked to find the output voltage in terms of or by using the superposition principle. So just remember the principle and write it down carefully and go step by step as we always do in circuit analysis. And for problem 2 we're asked to find the output voltage also, but using source transformation only. So pay attention to signs and best of luck. So I'll allow you to pause the video and give these 2 problems a try. Okay, so assuming that you've tried these problems, I'm going to go ahead and solve number 1. So we're asked to use superposition. So what I'm going to do is first to write out what this solution should consist of. So the first thing to note is that we have 3 different independent sources, and by superposition we have to turn everything off except for one source at a time. And so we know there's going to be 3 different combinations of scenarios. And so the first case, we could say the order really doesn't matter because they're summing. We're going to sum the solutions at the end. So the first case we could say is when, let's say when the current sources are all zeroed out. So IS1 is equal to IS2 is equal to 0. So that's the very first case. The second case you could say is when Vs is equal to 0. Sorry, let's do it differently. Vs is equal to IS1 is equal to 0. And the third case is when Vs is equal to Is2 is equal to 0. So let's think about it. At any given time, we're crossing out. So for the first case, we're crossing out the current sources. Let's write these out case by case. First, we cross these guys out, keep one on. Then we cross out the voltage and one of these guys, current sources. Then we cross out this guy and this guy. So that makes sense. So I'm going to go ahead and pause and write down the circuits, the simplified circuits. Okay, so we have the simplified circuit for the first case. Now I could make one more simplification. Before doing that, let's talk about what I did. So I simply opened the current sources, and by doing that, they just do not inject any current into the circuit. So you can just pretty much ignore them, cross them out, and you get this circuit here, simplified circuit. Now I can just combine a single step and just make these 15 ohms by adding them because they're in series. Then I'm going to go ahead and take the parallel combination of 15. So let's just say that. Let me just go ahead and clean this up and call it 15. Okay, so now I'm going to go ahead and take the parallel combination of 10 and 15. I'm not going to write it out multiple times because we have really low space. So okay, so having simplified all the resistances, we can see that we have a simple voltage divider now. And so this particular output is going to be the source, which is 10 volts, times 2 over 2 plus 6, which is 10 times 2 over 8, which is 10 over 4. That is roughly 2.5, or it actually is just 2.5 volts. So what we just found is the effect of only the voltage source at the output. Now we're going to go ahead and do the simplification for the current sources. So case 2 where we short Vs and open Is1. Okay, so once you short VS and open IS1, you essentially get the circuit down here. Now it's your choice how you want to solve this. You could either do source transformation or some sort of Y delta transformation. I chose to do a delta to Y transformation here, just to kind of bring back those ideas and kind of make it more complicated, because I'm sure you can choose the easy way out, but I'd like to do it more complicated so you get more practice. So by doing the delta to Y transformation from lecture 8, if you don't recall them, I recommend you to go watch them. But what I'm doing here, I see a delta here immediately, because you can imagine that's a resistor here. So we have a 5, a 10, and a 10, and of course you have the rest of the circuit. That's one thing you need to do as an electrical engineer, is to be able to see these very quickly, kind of recognize the patterns. So you can see I can just kind of move the branches around and get this to look like a delta. And so I want to turn this into from a delta to a Y, so the Y would look something like this. And I'd want to convert these, and I've gone ahead and done the conversion. If you recall, it was basically this resistor is going to be the multiplication of the adjacent resistors in the delta configuration divided by the sum of all the delta resistors. So in this case it would be 5 times 10 over 10 plus 5 plus 10, which is 25. So 50 over 25 is 2. You can see that here. And for this resistor it would be 10 times 10 over 25. That's 100 over 25, which is 4. And so on and so forth. So I've gone ahead and done that, and once you do that, you see a current source going up here to this particular node. I'm going to call that Vx, and I'm going to do a simple KCL. So I'm going to say that's the current going there, and going there, these currents. And if I do one KCL equation, I get that, now this is V out when Vs equal to 0 equal to IS1. So for the first equation I have Vx, let's see here, I have 2 amps is equal to, because that is the current going into that node, and these guys are leaving, the currents are leaving there. So I have 2 amps going in, Vx over 2 ohms leaving, plus Vx over 4 plus 2, because that entire node, that entire branch is 6 ohms. So what we get is that's 2 amps is equal to, let's find the common denominator. We have, let's see, multiply by 3 here, we get 4 over 6 Vx. Let's see if that's correct. Right, that should be 4 over 6, which is just 2/3. We can cancel the 2 out, so that's 2/3. Cancel these 2's, and we have that Vx is equal to 3 volts. Now for the second equation, we can see that V out is whatever the current is in that entire branch. So Vx over 6 ohms, that's going to be the current going there, multiplied by that resistance 2 ohms. So that is Vx, which is 3 volts over 6 times 2. That's 1/3 times 3, that's 1 volt. So the contribution from that particular current source is going to be 1 volt at the output. Let's go ahead and do case number 3. Okay, so for the final case, I hope you can see the circuit. I'm really running out of room here. But for the final case, we have shorted out this voltage source, and we've opened up that second current source, IS2. So now we have this circuit. So what I'm going to do is basically, if you recall from before, I'm going to just move this resistor, the 10 ohm, I'm going to move it and bring it down here in parallel with the 5 and the 10. I'm going to combine the 5 and the 10 to get 15. Once I do that, I have basically a 15 and a 10 in parallel. Then I have a current source. Then all of those are going to go like so. So I'm going to have the 10 and the 15, I'm going to combine them, and I'm going to get a 6 in parallel, which is this guy. So I have the 4 amps going like so. So if you don't recall why we can do this, just go back to the previous examples. these are equivalent because the KCL does not change. This current still has to go to that node, and if you move it around, the current still travels and goes into that node, so there's no problem doing this. And once you do that, then you can source transform this particular current and resistor pair. Remember that the resistor remains the same, 6 ohms. The voltage becomes 6 times 4, which is 24. And just remember that you can drag this guy, kind of bring it down here, but keep track of the signs. You get a minus and a plus in this manner. You can do a voltage divider. It's kind of funky looking. It's kind of on its side, but that's no problem. Basically, so negative V out is going to be 24 volts times 2 ohms over 6 plus 2, and so V out, and this is the V out under the special condition, let's say condition 3 to make it easier to write. So V out under condition 3 is going to be 2 over 8, which is 1/4 times 24, but it's going to be negative, so negative, what is that, 1/4 times that, that's going to be 6, right? So negative 6 volts. And to summarize everything, V out is going to be the sum of all 3 conditions. So it's going to be 2.5 plus 1, which is 3.5, minus 6. So what we're going to have is, so what I'm doing is basically just summing all the final answers. Where is this other guy? That's 1 volt, that's negative 6. So 3.5 minus 6, you're going to get negative 2.5. We're going to verify this shortly. Okay, so here we see the LT-SPICE simulation. You can verify that everything is correctly placed here. 10 volts, negative 2 amps going down, which is 2 amps going up. Label V out is what we're going to look for, and let's go ahead and run the simulation. You can see that V out is indeed negative 2.5 volts. Going down here, we get negative 2.5 volts, so that was done correctly. Now I'm going to go ahead and solve problem 2. I hope that you've given it a try. So we're going to use source transformation to solve this problem. So let's see what we're going to do here. So looking at this, I know that I'm essentially going to have, at the very minimum, I'm going to have 3 different source transformations in one step. So let's go ahead and do that, keeping close attention to the signs. Okay, so essentially what I've done is I've taken, I've kind of noted the direction of each current source and performed a simple source transformation. So if I look here, for the first case, I have 4 amps going into, I kind of just isolate them and think of these terminals by themselves. So A and B, for example. I have 2 ohms here. I think, what is that equal to? So the current is going this way, and so I'm going to have a voltage drop looking like that. And when I measure the voltage with some probes at these terminals, I would see a voltage in that fashion. So I would have the same polarity as you saw here. I'm going to have 4 amps times 2 ohms, which is 8 volts. Then I'm going to have 2 ohms in series. And that's what you see on this end. I've simplified the circuit to what you can see down here. Similarly for this guy, you would have 3 amps. You have to always, in electrical engineering, you have to isolate things and do divide and conquer. Don't get too worried about the big picture, just do small steps. So that is equal to, I see again the current's going this way, so my voltage drop is this way. And so that is equivalent to a voltage source that is in this direction. That is 3 amps times 10 ohms, which is 30 volts, and the same resistor. And let's see, that is what we have indeed over here. Now lastly, I have 5 ohms, 5 amps. All I care about is what's going on between these two terminals. The current's going this way, voltage drops this way. I have that
being equivalent to plus minus. That's a 5 ohm. 5 times 5 is 25 volts. That is a direction that you can see here. So everything else remains the same. Now we're going to do so what you might notice is that for source transformation, you essentially either want to get everything down to a single mesh like so, or you want to get everything down to a single node so that things are simplified a lot. And whether you want to get a singular mesh or a singular node depends on what kind of issue you have, what kind of problem is given to you. So in this case, when I looked at this, I saw that I have a resistor here and a voltage. So I know I'm going to need some sort of a mesh analysis because I need to find the voltage drop across it. And it's in series with this voltage source, so I'm thinking meshes are probably more appropriate. And so I want to turn everything such that I get a mesh. And by doing a source transformation for these current sources, I get voltage sources in series with resistors, and I can get a singular mesh. Now, if I go further, recall that for a given mesh, the order of the voltages don't matter, so long as you keep the signs, you keep track of the signs and do it carefully. So if you look here, you would see that I kind of assign a current flow direction, a mesh current flow, and I just make sure that everything is kept in track. So looking at here, I just start at the -30 and go up. So I see -30, I'm only looking at voltage sources. I see a -30, -25, -20 plus 8. So I think to myself, okay, that's -30 minus 25 minus 20 plus 8, and that gives me a -67. But I'm going to recall the direction of the current. So the current's going clockwise, so I know when I hit a negative, it's going to have their orientation as below. So I'm still kind of following the clockwise current. I follow the clockwise current and hit a negative, and that's the orientation in which my -67 should be. So the negative simply means where my clockwise current, which polarity it meets first. So it meets a negative in this way, so it should be in the same direction as the current. That's all that means. I do that, then I combine all the resistors because I know that they share the same current. And so we're exploiting these properties of circuits, the very basic properties of series and parallel circuits. And that's why you have to really master the fundamentals. That's the purpose of this, is that you have to be very comfortable and be able to just quickly use these building blocks and fundamental concepts. So I combine the 10 and the 5 and the 2 and I get a 17, but I don't touch the 1 ohm because I know I need to find a V out across it. So the next thing I do is that, okay, now that I have a single very simple mesh, I basically say, okay, my V out, I know it's going to be negative because the mesh current flow is going clockwise, but it's going against the passive sign convention, so I already know I'm going to have a negative sign. So -1 times the voltage over the total resistance, so volt over resistance times that particular resistor that it's passing through with the negative sign. So that is the final answer. Ohms cancel out, and we get that V out is equal to 67 over 18, which is roughly 3.722. So V out is roughly 3.72 volts. Now let's go ahead and use LT-Spice to verify this result. So here's the original circuit. Let's go up here and compare side by side. You can see that everything's the same, but the ground, I've selected it to be here. That is not a problem. With the ground being put at this node, then this node is ground, and so Vx is going to tell us the voltage drop across the 1 ohm resistor. So if we press run, we see that the fourth resistor R4 is going to see 3.722 volts, and that is indeed what we calculated. Now the sign is incorrect, but that is again because of the way that resistors are defined in net lists, and so they're kind of defined as, if you recall from the earlier lectures, I believe lecture 6A or B, when we talked about LT-SPICE and netlist, we see that resistors are defined as the end point and then the initial point, and so the negative sign has to do with that in this case. Okay, so good job for following along, and I hope that you've gotten something out of this lecture. I will see you in the next lecture.